How can we go about showing that, just using that negative angle identity and with the sum of signs, which is that first one, basically prove the second identity over here. So I kind of got just a little bit of head start here. So, we didn't have to keep going back to our textbook and looking at it over and over again. So you can see basically they're telling us, okay, this is what we are giving you, sine of u minus sine of v, using the negative angle identity. So this is where, remember, we take the negative sign and put it inside to make the angle itself negative. So we went ahead and took this negative and put it into the sine of v. So that ends up becoming sine of negative v. Now the idea is using this sum to product identity, we need to prove using this identity, using these rules here on the right-hand side, that this guy will in fact work and give us the same result as this second one over here. So we have to basically show this will come out to be true using that negative angle identity. So I will get you guys started over here, but I do need you to, kind of try and see how this will, work through. How do you go forward with that? So let's take a look here. So basically what you are doing is, sorry, I just realized you guys couldn't see this. So this is what I'm talking about. Using the negative angle identity, you are rewriting sine of u minus sine of v as sine of u plus sine of negative v. So this is what I was saying, that you're taking this negative sign and putting it inside of the angle to make it sine of negative v. And now using this sum to product identity of sine of u plus sine of v, how do you apply that to this sine of u plus sine of negative v? So when you are rewriting it, basically you have to think about, okay, everywhere that I have sine of v, I need to replace that with sine of negative v, right? So when you are writing this out in this sum to product identity, you have 2 times sine of u plus, instead of v, we will replace that with negative v, right? Because that's what we have over here. So same thing with cosine of u minus v, you will take that v and replace it with negative v. And then how will you clean that up so that, we can prove that our identity will in fact match what we have on the right-hand side over here for that number 2 identity. So this guy over here. So you just have to make it look like this. So I'm going to give you guys a minute to just work that out and make sure you are able to verify that. And then, we can just do a quick follow-up to make sure everybody was able to get that. So basically everywhere that you have sine of v and you're plugging in negative v where originally the identity has a positive v, and then you should be able to just, work through the math and make it work. And honestly, I think it'll be a matter of just cleaning up your signs, because they're not really having you, prove anything, right? There's no proof for the identity here. Okay, Masab, I see your answer. So again, guys, wherever you have v, you are replacing that with negative v. Okay, Andrew, I see your answer in there as well. Okay, very good. So yeah, like I said, it's basically just a matter of cleaning up your signs in here. So you have u plus negative v, so of course positive and negative becomes negative. So you end up with u minus v divided by 2. And then for the cosine function, um, we have u minus negative v. So of course negative and negative becomes positive. So you end up with u plus v divided by 2. And I think in the identity, is that order the same or is it switched? Is cosine in the front? No, they do have sine as the first function and then cosine. But again, multiplication is cumulative, right? So it really doesn't matter if you have the sine function written first or the cosine function written first. But basically, you can see the idea here behind this activity is, we've already proven that that first identity works, right? We already went through all that process of proving that sine of u plus sine of v, ends up giving us this right-hand side product. So once you have that identity proven, honestly, we're just building up on that. And we are saying instead of starting over and trying to prove the second identity, we can just use the negative angle identity, take that negative sign, move it inside of the sign of v function, making it sign of negative v, and then basically just following the first identity and helping to show that this in fact does work out the way we want it to, and you are done. And that's kind of the beauty of this, is that we don't have to go about reproving the second, third, fourth identity if you've already done it for the first one. So just simple stuff like that. And these are the same kind of techniques you will be using when you are solving equations with trig functions, right? We don't have to start at the beginning and start from the basics, right? We can kind of build up on what you have already learned using the different identities, different rules, and keep going from there. All right, guys, so let's take a look at how we can apply this sum to product identity. So we're going to do the evaluation example first, and then you will see we're going to try and prove a different type of identity in example 10. So this one, we're going with degree angles. So here you've got cosine of 15 degrees minus cosine of 75 degrees. And give me a second. I did not open up our unit circle. Let me get that guy open. So in the unit circle, you will see 15 degrees and 75 degrees are not two of the known angles, right? So it's not like we can just, use the values from the unit circle and then evaluate what cosine of 15 and cosine of 75 degrees will be. So, again, we just use this idea of, okay, so cosine with the minus sign, that's going to be that last identity is going to be -2 sine of u plus v divided by 2 multiplied with sine of u minus v divided by 2. So using that, you can see we've got -2 sine of 15 plus 75, which of course will add up to 90 degrees. So 90 degrees divided by 2 will of course give us 45, and then sine of 15 minus 75 will of course give us -60 degrees. So -60 divided by 2 will end up giving us negative 30 degrees. And then we can basically, and again, they're kind of skipping some of the steps, but you've got -2, and then we've got sine of the positive 45 degrees. So of course, sine of positive 45 is going to come from this angle here. So you can see sine is going to be square root of 2 over 2. So that's what we will have from that function, square root of 2 over 2. And then you've got sine of -30. So remember with the negative angle identity, and we just did that in the try it now above, you can rewrite this guy as negative on the outside and sine of 30 degrees, right? So just bring the negative sign here, and then you can evaluate what sine of 30 degrees is going to be. And of course, coming back to our unit circle, you will see sine of 30 degrees is going to be that 1/2. So keep the negative sign from our negative angle, and then you have 1/2 here. So of course, 2 and 2 will cancel each other out. Negative times negative will end up becoming positive, and then you're just left with square root of 2 over 2, and that's, how they're cleaning up that final answer here. So this is just using the sum to product identity to help us, simplify angles that are not known within the unit circle, and you can use them to, come up with a result. Now, like I said, we can also use this to prove a more complex identity, which is kind of what's happening in example 10, but I just wanted to take a second to see if anybody had any questions on number 9 before we move forward. Okay, not seeing anything pop up. So you can see how on example number 10, we have cosine of 4t minus cosine of 2t, and that whole thing is being divided by sine of 4t plus sine of 2t. So of course, cosine of 4t minus 2t, kind of the same thing we did in example 9. So you will see this guy will break down into -2. So you've got -2 here, sine of 4t plus 2t, which of course will add up to 6t. 6t divided by 2 will give us 3t. And then sine of 4t minus 2t will of course be 2t divided by 2, which will end up giving you just a single t. So as we go to the next step over, you will see that's where we ended up with 3t over here for the first sine function and just t on the second sine function. Now for the bottom of our fraction, we've got sine of 4t plus sine of 2t. So this will of course come from that very first identity. So this one you can see is going to be +2 sine of u plus v divided by 2 times cosine of u minus v divided by 2. Okay, Mickey, no problem. Thank you for letting me know. So using that, you can see we now have +2 sine of, same thing, 4t plus 2t over 2. So that's 6t divided by 2, which will also end up becoming 3t. And then cosine of 4t minus 2t will be 2t divided by 2, which again cleans up into just a single t. Now, once we have this identity cleaned up, then you can see we have a sine of 3t on the numerator, sine of 3t on the denominator, so they will cancel each other out. We have a 2 on the numerator, a 2 on the denominator, so they will cancel each other out. Now that negative sign will stay, and then you of course have the sine function and the cosine function, which of course sine over cosine we know is the tangent function, and then keep that negative sign, and you are able to prove that, this identity does in fact, the left-hand side equals the right-hand side, and we are able to prove it. So again, just using the sum to product identities, right, to help us take something which is a more complex identity and break it down so we know that in fact does work for us. Alrighty, guys, again, take a second to see if you have any questions on that, and then we'll get into this example over here, which is basically looking at, solving the equation using these sum to product identities. But I'll give you, and I think that's the last example in this section, but I'll give you another just a second to see if you had any questions on number 10. Okay, so I'm not seeing anything pop up just yet, but let me know if something does come up. All right, so here you can see we are given sine of pi times t plus sine of 3 pi times t is equal to cosine of pi times t. And they're asking us to find all the solutions where your t value is going to be between 0 and 2, not including the 2, but obviously including the 0. So for equations like this, and this is kind of where I've talked about this before, trial and error kind of situation comes in, because do we start on the left-hand side and try and see, like they're talking about, one option would be to combine the two sine functions on the left-hand side of the equation. The other option would be to move the cosine to the left side of the equation and then, combine it with the sine function. So basically take that cosine and move it to the left-hand side, kind of would be the more straightforward approach to go to. Should we just start on the left-hand side, move the cosine function to the left-hand side and go from there? So it will just be a trial and error. You try one way. If it does not work, then you go and try it the other way. So in this example, they are obviously starting by combining the left-hand side here, which of course will be, since you are adding two sine functions, we would obviously be using the sum to product identity here, which is that very first one on the top, right? So using that, we will go ahead and combine the left-hand side. So as you can see, we start out with taking 2 times sine of pi t plus 3 pi t. So that's, of course, you can think of there being a coefficient 1 in front of the pi. So 1 plus 4, 1 plus 3 will give us 4. So that ends up becoming 4 pi t divided by 2. So of course that reduces down and becomes 2 pi t. So that's where this guy is coming from. With the cosine function, you can again do 1 pi t minus 3 pi t. So 1 minus 3 is -2. So you end up with -2 pi t over 2. So your 2's will cancel out, leaving behind -pi times t, right? Now, again, guys, remember how the cosine function absorbs that negative sign. So that's why the cosine of -pi t ends up becoming just positive pi t, because the cosine function is absorbing that negative sign. And then, of course, the sine function will stay the same. So once we end up at this stage over here, you've got 2 times cosine of 2 pi t times cosine of pi t. Now we are going to take this cosine function and move it to the left-hand side. So we start by subtracting cosine of pi t. Now, this is kind of where I want you guys to just be a little bit careful. So basically at this point, you have something that looks like 2 times the sine function, and I'm just going to call it x for now, times the cosine function, which is y, minus the same cosine function is repeated, right? It's cosine of pi t. This is also cosine of pi t. So basically, you're kind of bringing that same value in. So since you have a common factor between those two terms, we can basically go ahead and factor out that common term, right? So we can kind of take that cosine of pi t as my common term, take it outside, and then whatever is left behind, we put that in parentheses. So that's the same thing that's happening here. You factor out the cosine of pi t from that whole left-hand side of the equation, and you will see we will be left behind with 2 times sine of 2 pi from that first term. Since we took cosine of pi t from that second term outside as our greatest common factor, you use -1 as the placeholder, right? So that's where -1 is coming from. And remember, the idea is if you were to go back and distribute that cosine of pi t back into the parentheses, we should come back to the step above it, right? So that's where we need to have that -1 as the placeholder so that we can, go in the reverse direction and still come up with the same result. So that's what's happening here. So we basically just factored out cosine of pi t, and then you're left with 2 times sine of 2 pi t minus 1. And then, of course, with this guy being equal to 0, you would then take each factor and set it equal to 0, right? So that's kind of what's happening in the next stage, is we're going to use that zero factor theorem, or they're calling it zero product theorem here, and set each one of these equal to 0, and then you go about solving from there. So before we do that, let's talk about, what the period of these functions is. I'm actually going to go ahead and erase my writing here, and let's scooch down a little bit. So as you can see, the cosine function is given to us as pi t. So remember, when you are figuring out what the period of the new function is, you take our little equation over here. So you take the original period for the cosine function, which is of course 2 pi, and divided by that b coefficient, remember, which in this case happens to be pi. So 2 pi divided by pi, of course, simplifies into 2. So we're basically saying the period of this cosine of pi t function is going to be 2, which basically tells us then within that cycle of 0 to 2, we're going to have one revolution, right? Or one full cycle of this cosine of pi t function, which is what they wanted us to find the solution for, right? Remember they told us t is between 0 and 2, not including 2. So that kind of works out well with this period of the cosine function here. Now we can go ahead and set cosine of pi t equal to 0 and solve that. So you will obviously see we're doing the u substitution here. So cosine of u equal to 0. And then again, we know cosine is going to be 0 at the pi halves angle, and then of course at the 3 pi halves angle over here. So that's where these two guys are coming from. Go back and undo the substitution. So replace the u with pi over t, and then you can just simplify that. So think about this. If you have pi over t equals pi halves, or, on the other side, we have pi of t equal 3 pi halves. Uh, we would obviously get t by itself, so divide both sides by pi. Or you can also think about it as multiplying by 1 over pi, if that, helps you visualize it better. So if you're multiplying both sides by 1 over pi, or divide by pi again, like I said, whatever visualization works for you, well, the pi and pi will cancel out, leaving us with 1/2 for that first part, and leaving us with, 3/2 for that second part. So that's where you can see the t equals 1/2 and t equals 3/2 is coming from, because we got rid of pi, from both sides of our equation in a way. Okay, so that's coming from the cosine of pi times t function. Now, our second factor is this guy over here, which is the 2 times sine of 2 pi t minus 1, right? So again, looking at the sine function, you can see this has a b value of 2 pi. So again, finding the period. Okay, Phoenix, yeah, thank you for letting me know. So calculating the period for the sine function, you will see original period of the sine function is going to be 2 pi, and then the b value in this function is also 2 pi. So that, of course, ends up giving us a period of 1. So that actually means, since it only takes one cycle or one revolution from 0 to 1, that means from 0 to 2, we will have actually completed 2 cycles for this function, right? And again, remember, guys, we're keeping it 0 to 2 because that's what they're asking us, right? For the t value to be between 0 and 2. And that's why we're changing that to 0 to 2, which gives us the 2 cycles. So now let's take a look at what happens when we solve that. And so here you will see that once we set this equal to 0, you'll go ahead, move that 1 to the other side, go ahead and divide by 2. So you end up getting sine of 2 pi t function by itself, and that's equal to 1/2. So again, we start by using u substitution. And now we're okay saying sine of u is equal to 1/2. And again, where is the sine function going to have a value of 1/2? And you will see that happens at this angle of 30 degrees, or pi over 6, since we're keeping it in radians. And then the other one is happening at 5 pi over 6. So 1/2 over there. And I think those would be the two angles. So pi over 6 and 5 pi over 6. So once you have those angles in there, then we can go back and undo our substitution, right? Just saw a message pop up. Okay. So yeah, now undoing our u substitution, you will notice that this is now giving us, oh, okay, hold on a second. It looks like one of your classmates is. Um, yeah, I think that worked. Guys, please make sure your cameras stay turned on, okay? Do not turn them off. So sorry, before we actually undo the U substitution, since we are talking about two cycles, right? Because this sine function only had a period of one. So between 0 to 2, it will have two cycles. So we do actually need to take those angles into consideration for the second cycle here. So for the first cycle, we got pi over 6 and 5 pi over 6, but we need to repeat that, right? Go one more revolution. So that's where you will see we are adding 2 pi to create that second revolution. And so the new angles from that second revolution will come out to be 13 pi over 6 and 17 pi over 6. So when you undo the U substitution, you will see we need to do it at all four of those angles as you're calculating here. So you will end up dividing by 2 pi to get the t by itself, right? So for each one of these angles, you would be dividing it by 2 pi, and you can see how the pi's will cancel out, but then you end up doing 6 times 2, which is why your denominator changes to 12 over here. Okay, so now you can see we technically end up with a total of 6 different values for t, because remember, 2 of those came from the cosine function from that first half when we solved, cosine of pi times t, and that had given us 1/2 and 3/2. And then you have your four angle or t values, I guess, in this case, from the sine function. So you can see in the graph also, they're showing you that graph from 0 to 2 on the horizontal axis. So you can see how the cosine function met at crosses the x-axis at, let me change that color, crosses the x-axis at 1/2. So we have the 1/2 from there, and then remember it was 3/2, which is of course 1.5. So that's these two values over here coming from the cosine function. And then for the sine function, you have I think this should be 1/12. You should have 5/12. I think it's overlapping with the dot I have for 0.5. You should have the 13/12 because it will be slightly larger than 1. And then you will have your 17/12, which will be just shy of 2 on that side. So you should see those total 6 points. And, again, there's a little bit of overlap happening at the 1.5 and the 0.5 location, but you have your 6 pairs where the graphs are crossing the x-axis at. So again, how do we use the sum to product identity to help us solve an equation? And you will see a lot of these techniques we had seen in the previous sections. The only thing that happened was how do we combine the left-hand side, the two sine functions to, move forward. And that was the approach that seemed to work. And we didn't have to do the second approach that they were talking about initially. Okay, any questions, any part of this example, I guess that did not make sense, or you need me to break down any further? Let me just give you guys a second to look at that. In the meantime, let me go ahead and open up our page for the next section. Okay. So if you do not have any questions, we can go ahead and get into our section 3.3 or your textbook section of 7.3. So this one over here, you can see again, we're building up on identities, right? Because that's kind of what this chapter deals with, is just different identities being introduced. So sometimes we can have examples where you have Wyatt, we actually do not have a try it now on that, but let me see if we can find a similar example. Okay, most of these are proving identities. I think these are the equations up here. Okay, so they're saying find all solutions. I'm looking at that very top of the page over here. So we can do something like that. How about we do the first one, because we actually have not talked about the cosine plus the cosine identity, which, sorry guys, I know I'm doing a lot of scrolling here. But the only identity we kind of did not break down was this guy over here. So let's take a look at that number 31. So we, get a chance to look at it. So they're asking us to do cosine of 5x minus is equal to minus cosine of 2x. So let's go ahead and get that guy over here. This is weird. The chat keeps showing me there's a message, but when I click on it, it's not showing me a message. So I'm not sure why. I guess it's ghosting me. Oh, is it not letting me add a page to it? I just want to add a page to that. Okay, sorry, this is weird that it's not letting me add a page. Alrighty. So let's copy that guy over so you guys can get a little bit of practice on that. So this was number 31. And we are given cosine of 5x equals negative cosine of 2x. Okay, so obviously the first thing we want to do is go ahead and move that cosine of 2x to the left-hand side. So, we would go ahead, since it's minus cosine, we'll go ahead and add it. So we can do cosine of 2x and add that to the left-hand side. So that will end up giving us cosine of 5x, that should be an x, plus cosine of 2x. And then, of course, you will end up getting 0 on the right-hand side. So essentially, these guys just cancel out. Okay, and then applying that property for the identity of cosine u plus cosine v, and you can see this is 2 times cosine of u plus v divided by 2 times cosine of u minus v divided by 2, right? So applying that, we will have positive 2 in the front, cosine of 5x minus 2x divided by 2, and cosine of 5x minus 2x divided by 2. And this time I did see something pop up on chat. So how will we move forward from there, guys? All right, very nice, Andrew. So you've already got that sorted out. That's amazing. But remember, guys, we are trying to find all solutions. Remember, they said find, is it going to let me? Okay, let me go back to the example. So we're basically trying to find all solutions. So make sure, we're thinking of this as solving an equation. Oh, yeah, it is supposed, did I put minus on both of them? I did, didn't I? Sorry. Yes, it should be plus. So yeah, just go ahead and clean that up. So of course, 5 plus 2 will be 7. So that becomes 7x divided by 2. And then of course, on this side, 5 minus 2 is 3. So 3x divided by 2. So again, think about this. You are trying to solve this as an equation. So we have to figure out what the values of the cosine functions are going to be. So where would we go next from here, guys? Oh, okay, Mickey, thank you for letting me know. I did not realize it was snowing. It is pretty overcast where I'm at though. So again, guys, obviously we would start by dividing both sides by 2, right? Go ahead and get rid of that coefficient. So divide both sides by 2, which will of course just leave us behind with the 2 cosine functions. So you would have 7x over 2 for the first cosine function, and then 3x over 2 for the second cosine function. And just like we saw in the previous example, you would of course then have to think about what is going to be, oops, sorry. There we go. What is going to be the period for each of those cosine functions? So we want to think about that, and then of course figure out what the zero factor property or the zero product theorem or whatever your textbook called it. I call it the zero factor property. Will be. So can you tell me what the period of the first cosine function is going to be? So remember again, period is going to be the original period for the cosine function divided by the b coordinate, right? So in this case, the b coordinate is of course going to be 7/2, right? So how would you clean that up, and what does that answer come out to be? Yeah, and Andrew, the pi will stay, right? Because in this case, the pi is not canceling out. So yeah, you will take 2 pi, which is the original. And then remember, you can just invert that fraction and change it to multiplication. So very nice. Yeah, it is going to come out to be 4 pi over 7, right? Because you can kind of think of that guy being over 1. And then for the second cosine function, we had 3x over 2 for the value in there. So what does the period for this guy come out to be then when you clean it up? Yeah, make sure we're getting the correct answer here, guys. A lot of you are either leaving the pi value out, or we're not multiplying the 2, because it's not canceling out, right? Because it's a fraction on the denominator. Yeah, very nice. So this will actually end up becoming same thing like we saw earlier, 4 pi over 3, because the 2 and 2 are not canceling out. They actually in fact end up multiplying each other. Okay. Yeah, so you can see the first cycle for the first cosine function is going to be 4 pi over 7, and then for the second function is going to be 4 pi over 3. All right, now we can take each one of these cosine functions and set it equal to 0. So we can start by saying, okay, cosine of 7x over 2 is equal to 0, or cosine of 3x over 2 is equal to 0, right? And again, if you wanted to use U substitution, you can use U substitution. So in this case, of course, we would then say, okay, if U is equal to 7x over 2, and this guy would be U is equal to 3x over 2, then you are figuring out what is cosine of U going to be for 0, and what is cosine of U going to be 0, which I guess those answers will come out to be the same, but then, it will change once we undo the substitution. So can you tell me the angles where our cosine function is equal to 0 at? What should the value of U come out to be? Where is your function going to be equal to 0 for cosine? We're looking for the angle measurement here, Jeff. So we're basically saying for which value of U, which means at which angle is the cosine function going to be equal to 0. Musab, very nice. Yeah, perfect. Because remember, again, with the unit circle, you can see that's going to happen. Cosine is 0 at angle pi over 2, and cosine is 0 at angle 3 pi over 2, right? So yeah, very nice. You're bringing those examples, those angles in. So pi over 2, and 3 pi over 2. And then, of course, when you undo the U substitution, those answers will change because right now those angles are going to be same for both of our cosine functions up until this point. All right, so now undo the U substitution and we are going to say, okay, 7x over 2 is equal to pi halves, or 7x over 2 is equal to 3 pi halves. Same thing over here. This guy would be 3x over 2 is equal to, obviously, same angles, pi halves. And 3x over 2 is equal to 3 pi halves. Now, my question to you is, before we go ahead and simplify those, get the values for x, using the period of both of our functions, what else do we need to do? How many angles do we need to go till we can get to that period of 4 pi over 7? Do we know what 4 pi over 7 represents? This is probably where I would use Desmos to get a approximation. So 4 pi over 7, you can see, is approximately 1.795. And sorry, what was that other one? 4 pi over 3. And you can see this guy is coming out to be approximately 4.188. So how many more angles do we need to find outside of, because we just did from 0 to 2 pi, because that would be the one original revolution, right? So do we need to add any more angles to the 7x over 2 function, and whichever, based on the period, do we need to add more angles to the 3x over 2 cosine function? So again, just using those approximations from Desmos, your 4 pi over 7 was approximately 1.795. And for the 4 pi over 3 was approximately 4.189. So do we need to add more angles to one or both? Yeah, Musab, very nice. So the second cosine function, cosine of 3x over 2, you can see that is going more than just one, well, it's not just within 0, to 2 pi, right? Because again, remember, if you, again, you should be able to approximate this, but if you are not sure, you can see when we go from 0 to 2 pi, in a traditional unit circle, we are at about 6.28. So you can see these guys are a little bit shy of that, but you do want to make sure that you are including all the angles in there. So there will be some adjustments, yeah, that will need to be made. So Musab, you said 3x over 2 function will need 2 cycles of answers, since it will be less than 2 pi for 2 cycles. So what would those angles look like? Again, think about this. 2 pi, if you're just looking at one unit circle, we go from 0 to 2 pi. And let me go back over here, because again, you should know, obviously, at this point, that this is where the 2 pi will end, right? So 0 starts here, and when you make a full revolution, we come back, and this is where you would find the 2 pi also. So the first one is approximately 1.7, and then the other one was what, 4 point something? Very nice, Wyatt. I'm happy to see that you're kind of thinking, okay, is that going to be outside of our value over here if we are only going to 1.7? Then is the angle 3 pi over 2 for the 7x over 2 cosine function, is that going to be out of bounds? So what do you guys think? Is the 3 pi over 2 out of bounds for the 7x over 2 cosine function, since this guy's period goes to 1.795? Andrew says yes, okay. And then what about for the cosine of 3x over 2 function? Are we okay with those two being in there? And again, guys, use your approximation. So you can see 3 pi over 2 comes out to be 4.71238898. And you can see that number is larger than, in fact, both of our periods, right? For the 7x over, what was it? 7x over 3. Sorry, the 7x over 2 and cosine of 3x over 2 function. All right, so can you tell me, once we discard those extra answers, what kind of x values are we looking at? So we are saying this guy is out of bounds. So this angle is out of bounds, and looks like it will be out of bounds for the 3x over 2 function also, because that was approximately at 4.189. So they are both going to be out of bounds. So what kind of x value are we looking at? All right, I'm seeing some answers come up. Okay, so Musab, you've got no, we do not need to use inverse functions here, Mickey. We are keeping, yeah, just basically simplifying it for the x value. All right, Andrew, I see your answers. All right, guys, let's go ahead and break this down. So we're trying to get x by itself, which means we need to get rid of the fraction 7/2. So you can invert that 7/2 and make it 2/7, right? And multiply that on both sides of your equation. So this will end up becoming same thing on the other side for this function also, right? So let's go ahead and clean this guy up. Okay, I see that. Give me 1 second here. So yeah, the um left-hand side will just end up becoming x, and then of course on the right-hand side you will see that in this example, of course, the 2 and 2 cancels out, leaving us behind with pi over 7. And then remember, guys, since they were asking us to find all the solutions, that means they were not restricting it, right? So we will need to use the period of our function over here. So since this one was coming from the 7x over 2 cosine function, you will actually be adding 4 pi over 7 times k. Remember how we talked about using the periodicity if you were finding all the solutions? So you will need to do that for the first cosine function. And then for the second one, of course, we would be multiplying this with 2/3. There we go. And then same thing on the right-hand side. So you will see again, this guy will end up giving us, come on. So yeah, these guys cancel out, leaving us with x. Same thing here, 2 and 2 cancels out, leaving us with x equals, like you guys said, pi over 3. And then this guy had a periodicity of, wasn't that 4 pi over 3? Yeah. And then same thing, because k will be an integer. So k is an integer. I'm just using the set symbol for integer over here. If you're not familiar with it, it looks like an I, but with like two central bars. So that's the symbol for integer. I'm a little bit confused on that 3 pi over 2, because we are saying this has a period of 1.7, and yeah, I guess those guys will need to be left out, wouldn't it? Alrighty, so looks like we're coming up with one answer from each of the cosine functions. All right, let me see. Again, do we have any questions, I guess, on the process of breaking this guy down? Because yeah, remember, since we are talking about all solutions, we're writing it with an integer because, if we said, okay, k is equal to 0, then your angle would just be pi over 7. But if k was equal to 1, then you would be taking pi over 7 plus the period of, going through that one cycle, right? So we would be doing 4 pi over 7. If you did k is equal to 2, then that would be 8 pi over 7. That would be getting added into your function, right? So that's kind of how, because they did not restrict your x value to be between, 0 and some other number, you have to consider it for all. So yeah, we're saying it's going to be an integer because, we can go around saying it can be a positive or a negative angle, right? Because all solutions does not restrict it to just positives. It can be positive or negative. Now you will see there are some examples here which are asking you for like just the first two positive solutions, right? So in that case, we would not be using the k being an integer idea because we would only stick to finding the first two positive solutions. But this guy was all solutions, so you have to take both positives and negatives into consideration. Now, the other thing I would also suggest to do is graph it to see did we do that correctly or not. So we can do y equals cosine of 5x. Yeah, so this form, the cosine of 5x plus cosine of 2x. So we did have pi over 7. We did have pi over 3. But it looks like, and that's kind of what I was worried about, that we were missing a couple angles there, because you will see we do have 3 pi over 7, and we have 5 pi over 7 as well. We've got pi over 0, and I think the 9 pi, 5 pi, 3 pi over 7 are just multiples of the pi over 7 example, but looks like we got the pi over 3, but we're actually missing the pi angle in there. Will 3 pi over 7 be a multiple of that? I don't think so. I think 3 pi over 7 will be an angle by itself, because the repetition should actually start happening from right here. So we are actually missing a couple angles in our calculation, guys. And I wonder if that happened because we left 3 pi over 2 and out of both of our angles here. So give me just one quick second here. Let's see what happens if we did actually solve for x with the 3 pi over 2. And let's just take a quick look at what would happen if we did simplify that. So we had 7x over 2 is equal to 3 pi over 2. So, you know, when you got rid of that and moved it to the other side, yeah, see, this is where you would end up getting the x equals 3 pi over 7, because the 2's would cancel out, and then we would do the multiplicity, sorry, the periodicity. And then on the other side, we had 3x over 2 is equal to 3 pi over 2. So again, you know, when you move that to the other side, we have 2 over 3. So you end up getting x equals 2 and 2 cancels out, 3 and 3 cancels out. So you actually just end up with pi. So I wonder, because my other thought, which was kind of running in the back of my mind, as we were erasing these, because yes, for the individual functions, they would not work. But, you know, if we look at this as a combined function, and that's why I wanted to look at the graph, you will see with the combined function, you know, our periodicity was at 4 point, what was that higher number? 4.188. So I am kind of thinking that these numbers need to be there as long as they are before 4, you know, on the x-axis or the horizontal axis, we should be able to include those. And that is the reason why I wasn't convinced that we needed to leave out the 3 pi over 7 and the pi, because obviously we can see that is where our graph is intersecting the horizontal axis at. So yeah, even though my initial thought was maybe we don't need to keep it because of the individual periods, but when you think about this as one entire function, it actually does make sense to keep those and not discard them, because you can see that is giving us 2 additional values here. And again, same thing, our k will be an integer. So we will need to include those in there. And this is kind of what I'm talking about. You know, a lot of these functions, you just kind of have to play around with them, look at them, you know, use the graph if graph can be easily derived. And, you know, so even though initially our thought was like, oh, maybe those are out of bounds, but then once we look at the graph, it kind of makes sense that, yes, for each individual function it is, but when we look at them as one equation, one combined function, it is still well within that period of the function, so we have to keep it included in there. So does that kind of make sense why we brought those other 2 angles back in? Let me go like take a look at your chat here. No, we still want to do the individual periods because we do need to know, what they will look like. But in this case, since it is going to be a combined function, we are going to keep the higher period for the entire equation, which of course comes out to be if you look at the original, which was cosine of 5x plus cosine of 2x. So in that case, we are going with the higher period. So anything smaller than 4.1, what was it? 4.189, we are going to keep those. So Musab, it's not about forced to use graphs. I think the graph is more of a checking technique, right? So we solved, yeah, so you're taking up the higher period. So we solved the equations, we got our x values. But like I said, kind of in the back of my mind, I had a nagging feeling because I was like, are we really supposed to exclude 3 pi over 2? So that's kind of what the graph did, was verified that we actually did not need to leave those two angles out, because when we look at the graph, you can kind of see, it's obviously one single composite graph. And in this case, we would go with the higher period of the 4.189. So as long as the angle measurements are falling within that period, you are okay to use those values. And that's what we did. So within one cycle of the original equation, we were able to keep all four of the examples. Yeah, so why the 3 pi over 2 is actually not the original angle. Remember, 3 pi over 2 is just for the cosine of u function. But as soon as we replace that u with 7x over 2 or 3x over 2, that angle changes, right? From 3 pi over 2, that angle actually ends up becoming 3 pi over 7. So if you look at 3 pi over 7, you will see that number is actually smaller than both of the original periods, right? So 3 pi over 2 is coming from the unit circle, but that's not the angle that we are using in our cosine of 7x over 2 or cosine of 3x over 2. Right. So you have to take that into consideration because that angle changes from 3 pi over 2 into 3 pi over 7. And what was the other one? Wasn't it just pi? Which of course pi is 3.141, right? Which of course is well within the second functions period. So we are able to keep that and use that in there. So yeah, that's kind of what was happening, like Wyatt mentioned, is that, we were kind of looking at the original values of these angles, pi over 2 and 3 pi over 2, which only work for the cosine of u function. But when we translate them into the 3x over 2 for cosine or 7x over 2, those angles change and they ended up becoming pi over 7, pi over 3, and then 3 pi over 7, and just pi, right? So they were within the original period for those two functions that we started out with, cosine of 7x over 2 and cosine of 3x over 2. So we do actually keep all four of the angles in there. All right, guys, again, any other questions popping up? Okay, so I'm kind of glad we got a chance to look at this example so you guys can kind of see, when you're working on homework, what that would come out to be. No, Wyatt, do not apologize. Like I said, I'm glad we got a chance to work on this example. So you guys also kind of got to see the process of, how do we go about solving something like this? Because, when you're looking at an example in the textbook, which is already worked out, obviously it becomes very easy. But then when you're trying to apply it to your own example, we do have to be careful about what we get to keep, what we don't keep, or do we bring in more angles in there, or we don't need to, depending on the periods of the function. So it's okay if we got delayed on section 3.3, we'll do that on Monday. So I guess we will stop here, guys. Obviously, as you can see, we will be getting into double angle identities with section 3.3. So we'll begin that on Monday. So I will stay back if you have Any questions? Please make sure you are working on that homework and try and get 3.1 and 3.2 by Monday, okay? All right, guys, have a great weekend. Be safe, everyone, and I will see you Monday morning. Bye, guys.